Nope. You have not missed anything yet. Okay, it's time. Let's begin. Okay, I'm hoping that my voice can be heard in my cell phone because normally we have a recording equipment, but today apparently there's nothing in the room. My name is Huebner. I'm Director of Services Architecture at Mirantis, but in reality I do a lot of storage, specifically Ceph, and I would like to talk about some of what I have learned over the last 10 years with Ceph in the field. I think that some of you, I see heads nodding, I think some of you have probably seen early versions of Ceph and have been feeling a little bit like that with trying to tame a monster with a ray gun, because this was exactly my first experience with Ceph. One of the customers that we had was constant issues with the whole thing. So today I would like to talk about multiple customer projects. I will not name the customers to protect the guilty and to ensure that we are not getting hit on the head with a baseball bat. So, first of all, what is Ceph? I mean, most of you probably know, but I want to go over it very quickly, so people who have not had any experience with Ceph will get a little bit of understanding. Then the next is, I will have a slide on history, specifically where we're coming from and what changes have been happening over the last few years. Then I have a bunch of lessons that I've learned from many projects that I've had in the field. Just to myself, I do both the planning, we do architecture of Ceph clusters, but I also am always involved in escalations when our support team has questions that have to do with Ceph itself. Then I typically am involved too, so I see the good, the bad, and the ugly. And finally, an outlook, what Ceph is good for today, what we can expect in the future. First of all, what is Ceph? Ceph is software-defined storage. It runs on standard x86-64 hardware or also on AMD64 hardware. I have seen both sides running. x86-64 is still more common than ARM64, not ARM64. And we have, but I expect that in the future we are going to see a lot more ARM-based Ceph, specifically as also vendors like NVIDIA are going to CPUs based on ARM. The gray CPUs are all ARM, and we are going to see Ceph clusters on nodes that have gray CPUs. So it is going to be a multi-CPU approach. It is distributed across multiple nodes. Typically, the better it is distributed, the easier it is to deal with. It is highly reliable and resilient to failure. We have had at least one customer who has done their level best to lose data on a Ceph cluster with a whole bunch of very ill-advised changes, and they have not managed, which is a testament to how stable Ceph really is. We had a whole bunch of cluster crashes, so the clusters were down, but once the clusters came back up, the data was undamaged, and this is really, that's the most important thing to me. If you have, you can survive an outage, you cannot really survive very well if your data gets damaged. And the worst of all, if data gets damaged in a way that you cannot tell what is damaged and what is not. So, as we are at Open Infra, of course, I get to mention that Ceph is very deeply integrated with OpenStack. Specifically, Glance works best with Ceph. Even our customers will have other storage for Cinder, like some sort of CERN or so, often use Glance for the except for the glance component, because glance on Cinder is not particularly good. The architecture is we have had a lot of problems with that. And the other thing is, Ceph is sort of like a Swiss Army knife. You can do almost anything that you want to do with it. It can be an object store, file store, block store, all three of them together, and it is fully elastic between each of the storage classes. So there is no allocation of 50 terabytes here, 20 terabytes there. This is just the Ceph cluster has one state of full, and that is how much overall of the capacity is taken. One thing that needs to be said is the data distribution in Ceph is never entirely ideal. So you will not see that the cluster is 82% full, so every node is 82% full. You will have nodes that are a little bit less and have nodes that are a little bit more full. But which is one of the reasons why it is not really very well advisable to run Ceph very close to the top, to what it is theoretically capable of doing. One more thing. If you want to protect your data, there's different ways of doing that. You have replication, which is the default in Ceph, but you also can define erasure coding, various protection levels of erasure coding. However, erasure coding has a rather considerable math component, which makes it, if you do a lot of very small writes with erasure coding, you will find out that the right performance is not particularly good. So for object storage, it is a very good thing. I would not use it for OpenStack, for like Cinder or Nova. And then finally, not nearly as scary as it's made out to be, I think a lot of people who have seen the early versions of Ceph, everything that was, let's say, before Luminous, they have seen their share of pretty hefty problems, and a lot of them became really worried and scared of Ceph just because the early versions were so difficult to deal with. And that was only part of the reason was that Ceph was actually that bad. There was also another reason, which is that Ceph on hard disks is a bit problematic, like almost any storage subsystem on hard disks that does replication, because the hard disk, if you have like a 10 terabyte hard disk or 20 terabyte hard disk, replicating all the data that is on that disk takes a very, very considerable amount of time and also a lot of performance, so you will see considerable slowness. So, yes. Well, the Ceph versions, I have installed Ceph manually several times. It was not a particularly pleasant experience, especially if you do something small wrong. It can lead to very complex errors that you cannot easily troubleshoot. And then the thing is also, and this is what I want to talk about today, is ill-advised design choices and operational methodology. So, first of all, how big or how small can a Ceph cluster be? I got the other day, about a year ago, I had a customer who said, can I run Ceph on 3 nodes? We have these monster nodes with, back then, 128 cores, 2 terabytes of memory. Can I take just 3 of them and build a Ceph cluster on? Yes, you can, theoretically. There's a couple of issues that you will encounter. One of them is that Ceph is not supposed to replicate within one node. The Ceph cluster cannot become healthy with less nodes than it has replicas. So if you lose one of those 3 nodes, the Ceph cluster cannot repair itself. Even if it's only 10% full, it cannot become healthy again until you add a third node to that. The second thing is the better you distribute Ceph, especially with flash storage, the less likelihood you have running into performance bottlenecks. NVMEs are faster than Ethernet, and so if you have a server chock full of NVMEs and you have only a limited bandwidth going out of that server, then you will find out that, that the limiting factor, or the limiting speed factor of this is not your NVMe or whatever storage you have in there. It is going to be the network bottleneck. If you have instead, you have like 5 nodes that do the same thing with a smaller number of devices, then you have the data traffic much better distributed across those 5 nodes, and the risk of bottlenecks decreases dramatically. Ceph also does not have particularly high hardware requirements. If you have 128 cores and you have only 10, 15, 20 devices, then you have the hardware is hefty overkill for Ceph. You will not get better performance out of it just because you have that many more cores. So the minimum that we have found in our in many projects that you should have, if you have a specific dedicated Ceph cluster, is 6 nodes. So this is a recommendation that normally you can find that the cluster can still replicate itself or can repair itself if you have 5 nodes out of 6, 5 nodes out of 6 surviving. So if you only have 3 nodes after node failure, the replication will be incomplete. And then finally, if you have only a very small amount of nodes available, we have customers who say, okay, we want like 8 compute nodes and 4 Ceph nodes, something like that. I tell them that converged is, in this case, is a better choice. Converged is a little bit of a mixed bag. We have had that also. We have in the past, we had Ceph running on hardware directly. And if you have like multiple daemons running on hardware and you have KVM, the libvirt, everything running on hardware on the same node, it becomes considerably more difficult to troubleshoot, which is why running Ceph in Kubernetes is actually a really good idea. You will see a little bit of performance loss, but you will not see enough performance loss, in my opinion, that it makes it more useful to run run everything directly on hardware. Next thing, old hardware. Oh, first of all, any questions so far? Yes? Please.
If you run it on Kubernetes, what is your recommendation then in the number? Is it still 6? Is 6 what?
I would normally recommend 6 nodes simply because you have a reasonable distribution. Each of your nodes has 16% of the total data of the cluster. The recommendation is not directly dependent on whether you have Kubernetes or not, because you're not losing like individual Kubernetes pods. Normally you would lose a whole server if you lose power or if you lose networking. So the recommendation is the same, because the effect, even if you're losing, like, let's say you have 6 containers with 6 storage devices behind them, but you lose the whole node, the end effect is the same as if you had 6 OSDs running on hardware. So the recommendation is the same. However, these 6 nodes can be, if you do not have a lot of OSDs, you do not have to spend a lot of money on hardware. You can use servers that cost, let's say, $3,500, $4,000, compared to, let's say, a server that costs $25,000 with 128 cores. So distributing the data a little bit better is typically worth it. So customers ask, can we reuse X-year-old servers? We are actually running Ceph on Xeon E5 systems from about 10 years ago. Runs fine, really not a problem. What is really a big problem, this is the elephant in the room, hard disks for the purpose of cloud, for the purpose of Kubernetes are obsolete. And here's the reason why. The hard disks have a physical limitation, how fast the heads can accelerate when they are seeking data. And if you have a long string of data that is distributed across your hard disk, then you will see it, more and more the seeks the latency caused by the seeds will impact your performance. So you say, okay, my drive is rated at 250 megabytes per second. If you try this with thousands of 4K storage trunk accesses, you will not see 250 megabytes per second, you see 5 megabytes, 10 megabytes per second. And that will make, if you're using, especially if you're using it in OpenStack, and you have 1,000 workloads competing for IOPS, you will see the difference very heavily. I mean, technically, flash storage is also not truly parallel access, it's also serial access. But however, its flash storage is so small, so fast, that you do not see that it seems to you as if you are looking at parallelity instead of serial. So one more thing is all the servers may have higher failure rates, but that's pretty relative in my opinion. A lot of people have older systems, and they by and large run fine. If you are looking for the highest degree of reliability, maybe not a good idea to run on old hardware, but for most purposes it will be sufficient. Okay, one thing though, older servers comparatively use considerably more power than more modern servers. So that it could potentially be, if you have large clusters, it could potentially be a good idea just to upgrade, because especially here in Europe, where the power is quite expensive. This is essentially, it's a math problem. So let's go to flash storage versus hard disk. I've already spoken about this quite a bit, but this is what I hear most often. Customer says flash is too expensive. Like you say, okay, 3 years, 4 years ago, the flash was considerably more expensive than hard disks. Nowadays, if you go and I did the research a few months ago because a customer asked me to give him actual numbers. And so those 2.5-inch disks that you usually use in OpenStack to distribute your IOPS in a sufficient manner, they are actually nowadays more expensive than a comparable flash device. And they are less reliable, they are drastically slower. You can see 250 megabytes per second, and this is only under optimum conditions and multi-millisecond latency versus 6,000, 7,000. It doesn't really matter very much. Megabytes per second and microsecond latency. The parallel access I already mentioned. And here's another thing, and this has stopped us in the very beginning when we had a lot of clusters that had hard disk. That was the journals. If you Ceph writes journals to basically keep the data integrity, especially in the case of power failure. And these journals are very high access, very small, a lot of very small writes. So what the customer started doing, and Ceph does support that, is to say, okay, I have one flash device and I have like 5 hard disks, and the flash device is going to write the journals for all those hard disks. It works, but it has been an operational nightmare, especially if that one flash device fails, then you lose the data on all those 5 hard disks. It has to be regenerated from the other devices, which is why I never really liked this solution very much.
Or you didn't get the journal size right and the partition size right, and then it starts overflowing onto the spinner.
You have the exact. I can tell you have
been there, done that.
Exactly. Thanks for the mention that yes, this is also a very considerable problem. So if I was to build a cluster today, even a test cluster, I would buy flash devices. So this is from a customer project that was 8-9 years ago, and it was an early Ceph version, hard disk based. They did have journals on flash. They had network problems time and again. They had hardware that would occasionally fail. hence the comments on old hardware. And so this is the interesting part here. In Ceph you can force Ceph to not repair itself. Ceph by default does. And customers tell me, well, but if I do that, then Ceph will start moving data anytime anything happens. Let's say we have a server that sometimes falls off the network.
Sorry, can you close the door?
Yes, good point. Yes. Peace and quiet. And I got a pointer. So basically you can tell Ceph in different ways to not fix itself. No out is the easiest when you tell the Ceph cluster if a device is not available. The Ceph cluster treats it as if it is still available, so it will not try to replicate the data from that device onto other devices. No rebalance. The Ceph occasionally looks across the multiple OSDs and can do some rebalancing work between those. And basically what these do is prevent Ceph from doing what it's supposed to be doing. And in this case, I even kind of understood the customer because it was our hard disk based, and it took forever. The customer was constantly churning, trying to repair itself, and the user access was a really big problem. But he was also wanted to run. I mean, if you set those flags when you have a replication storm, that's actually maybe a good idea. But he said, why don't we just run the cluster with these flags permanently on? And that led to catastrophic problems, meaning you have the cluster thinks that OSDs are still there, so you lose another OSD, you lose another OSD, and suddenly you're losing data. He did not actually manage to do that, but it came close a couple of times. At one time we had 1/3 of the cluster capacity with only one replica left, and with unreliable hard disks, I was sweating when we were repairing that. So normally Ceph clusters are very good at repairing themselves if something breaks. So these flags should only be used when there's a really warranted reason why we are going to deal with that. And so in flash-based clusters, of course, the problem has mostly vanished because even if something breaks and it replicates in the background, they have so much performance overhead with flash devices that you will see that or rather you won't see that anything is happening. Your users are not going to complain because the performance delta is too small for them to really notice. Okay. So, Ceph in secure environments. We have a rather big customer who is running with FedRAMP certification, and one component of that, of course, is the famous VNet encryption at rest. Encryption at rest is possible in Ceph. I personally recommend not doing it, and we also are not doing it at that customer. We are using encryption on the OpenStack side directly in Cinder, which means encryption at rest is simply unnecessary. But telling that to a bureaucrat who has no idea how the whole thing works is rather difficult. This is something that we really, there was really a lot of work being done to make the the bureaucrat understand that this is better than encryption at rest. Encryption at rest is pretty pointless anyway. The only thing that it really helps against is somebody stealing the storage. If you have you store unencrypted data, and you have only encrypted when it hits the disk, it simply does not cover enough attack vectors to be worth it, other than, of course, for the certification, which is why we are always coming back to our encryption in Cinder and Nova. It's reliable, it's fast, What you do need is Barbican because the keys need to be stored, but it really eliminates a whole bunch of attack vectors, like somebody hacking into a specific server and observing the traffic that's coming out of the virtual machine. If somebody manages to breach your virtual machine, then it's game over. But there's nothing that will protect you against that, really. I mean, nowadays there are ideas of even in the encryption in the virtual machine and encrypting memory and stuff like that. But realistically speaking, this is the best protection that you can get for your money. So, yeah, Barbican, and I personally would always recommend doing the encryption. By the way, Cinder and Nova are capable of doing both encrypted and unencrypted traffic, and here's the reason why this is important. Because if you have data that performance is tantamount and you do not really care about protection, then it is better to have unencrypted volumes because encryption always impacts performance. Whereas if you have data that needs protection, you can use a volume that is encrypted. You just have two different volume types in OpenStack, and you assign the right volume type to the virtual machine, and then you have no problem with that. Okay, usability improvements. Ceph has been constantly improved. I have to say I'm really impressed by the Ceph team about how they have been working a lot of the pain points that we have had early on. And at this point in time, I would say it is rock solid. It is as solid as commercial solutions. You always get this, but Ceph is 10 times slower than we are. This is not really true. It always depends very heavily on how you design the Ceph cluster. There's a few short pointers that I want to give. One of them is there are three main recommendations for performance. First of all, use a single CPU system only. This is the reason why is because in a dual CPU system, each CPU has its memory, and you cannot be guaranteed that the memory that you're accessing and also the network card that you're accessing is owned by the same CPU that your OSD code is running on. So it is possible, worst case scenario, the network card and the memory will belong to the other CPU. So you have data coming in through the network card, going to the CPU core. This is one-time latency, NUMA latency. Then it goes back to the memory, 2 times NUMA latency, back to the CPU for 3 times NUMA latency, and then out through the network card 4 times NUMA latency. So you see a considerable, even a very short latency becomes considerable if you multiply it often enough. Second thing is you should have a reasonable amount of memory. The Ceph team says, yeah, well, 3 to 4 gigabytes per OSD works, but we have seen performance improvements up to about 10 gigabytes per OSD. I personally think it's worth it, but it's up to everyone. It's still comparatively, if you have like a 8 terabyte OSD, 10 gigabytes of memory at today's prices is not breaking the bank. So it's relatively cheap insurance against performance degradation.
Do you have a recommendation on the number of cores per OSD with the
Cores per OSD. Yes, normally I would say 2 cores per NVMe is recommended. We will see from a single core to 2 cores. We will see a considerable increase. After that, the return on investment is getting
more about just during recovery operations.
It's not parallelized enough to benefit from a very large number of CPU cores. So basically, single CPU, 2 cores per NVMe, if you call it 3 cores per NVMe, memory about 10 gigabytes per NVMe, and then have reasonably fast network cards, 2 times 10 gigabit plus not cut it for flash-based. You will just have too much of it.
Do the
So-
CPU, the core requirements or RAM requirements change with the size of the NVDs now that we have like the 30 or 60 terabyte NVDs?
Good question. Here's the answer. It is theoretically possible to split an NVMe. To say, okay, I have an 8 terabyte NVMe, I run two OSDs on it. In the past, it was actually recommendation at Luminous and around that time, it was a recommendation to have up to 8 OSDs per back then SATA SSD. And nowadays it really does not make that much sense anymore. It does, partitioning an NVMe makes sense in another reason. If you have a large number of NVMEs that are all the same size, and you get newer NVMEs with a higher performance that are larger, it may make sense to split them in the middle to get something that is more uniform. So that's that. Okay, and one thing that I would also like to mention, our team has, we have always had a controller on top of Rook that is taking care of a number of idiosyncrasies from Rook and also the complexity of managing a large number of operational functionality of Rook. And this was a proprietary system, and we have recently open sourced this. It's called Pelagia, and it abstracts the Rook objects. It has custom resource definition that abstract Rook objects to something that is very much easier to manage in the field. So if you want to check it out, it's open source. You can try it out. It is not. It has been long running within our own system, and so I would say it's very reliable, and it's a good thing to look at, and also a usability improvement that I would recommend. What will the future bring? How much over am I already? When is the next talk starting?
3 minutes, the next stop.
Okay, I'm only going to take a couple more minutes. So first of all, what will the future bring? Ceph is with OpenStack, and why we run it with Kubernetes. One reason is because it works very well with Kubernetes, and it also brings something that is useful when you're running Kubernetes application, which is that it can mimic to be anything that you want it to be. You need some S3, put up a number of Rados gateways, use the same Ceph clusters like that. So Ceph integrates well with Kubernetes, and specifically also with Kubernetes apps. It works out well with other storage subsystems. What we have quite often now is that people say, okay, yeah, we are, let's say, Dell shop, we buy Dell storage. We have a small Ceph cluster that is providing ephemeral storage and images. And we have a large Dell storage subsystem that is doing similar, that's doing persistent block storage. So Ceph works really well in this context. Another thing, every year prices for flash storage drop. So we are going to see also both performance increase and a price drop of what this costs. And cost efficiency. I've done the math many times for many customers. Ceph is considerably cheaper, even though it does 3 times replication versus some, let's say, they have some sort of mirroring or so in USM. Ceph is considerably cheaper than pretty much all the commercial storage subsystems. So, just to recapitulate the lessons learned. Sizing and data distribution is critical. One thing that I forgot to mention before is also failure domains, making sure that you have the data distributed. If you have multiple racks, you should have it set up so that each rack is a failure domain, not each host. Second is, here's the failure domain design. Second is flash only. I would not. These days I would not do hard disk based Ceph, except for one reason. If you have archival storage that you want to keep for a long time and you want to use very large drives and you have slow influx of data, you do not have a lot of parallel access. Hard disk may still be worth it, but I would not use it for either OpenStack or Kubernetes for block storage. Let the cluster do its thing. Do not stop it from replicating data. This is your lifeline. If something catastrophic happens in the cluster by itself, encrypt at the source. Make sure that your valuable encryption don't go to the encryption on the targets. Go with the times. We still have customers with very old Ceph clusters, and I would recommend if you have one of those, have a look at what the cluster is doing, and maybe upgrading will really make your life a lot easier. And then finally, Ceph is highly reliable and it works with all kinds of cloud and container environments. I can only recommend having a look into how to design a Ceph cluster and play with it, and it is really production ready. Thank you very much.